Okay, so we take a lot of what we cover in 3.3, systems of linear inequalities, and kind of apply it to these real-world situations in 3.4 when we talk about linear programming. Okay, linear programming is used when we have to look at a function or a set of functions and talk about kind of how we can get the best value out of to fit these functions. Okay, so when we talk about linear programming, it's a method. Okay? Linear programming is a method. And it's used for finding the maximum or minimum value of a function. And when we're working with linear programming, that particular function applies to a particular set of conditions. Okay? And those specific conditions are called constraints. Okay? So one constraint is one of the inequalities in our system. We oftentimes look at a set of constraints or a system of constraints where we have more than one. Oops. So a constraint might look like something like that. Maybe that's what your constraint is. Okay? The minimum value or the maximum value based on this function relates to points that satisfy the constraint. So that function and the constraint work together. Okay? The feasible region is the solution to the constraints, to the set of constraints, to the, I should spell this correctly, to the system of constraints. Okay? That's a lot of heavy vocab. As we work through this example that I'm going to take you through, it's going to make a little bit more sense. Okay? But here's our feasible region, the solution to the constraints. Now we can graph a feasible region. Okay? Jillian is planning a green roof that will cover up to 600 square feet. She will use two types of plants, Blue Lagoon and Raspberry Red. Each Blue Lagoon will cover 1.2 square feet. That is an important information. You know what? So is this. Each plant costs $2.50, and Jillian must spend less than, oh, I love those words, less than $1,000. Ooh, Visto. Okay, must spend less than $1,000. And so you need to write the constraints and graph the feasible region. Okay, so we gotta write some equations. First of all, let's define a couple variables. B is gonna represent Blue Lagoon. R is gonna represent raspberry red. Okay, so now that we have our variables, we can set up our equations. First of all, automatically, we know that both B and R are going to be greater than or equal to 0. You can't put in negative plants. These two constraints, 1 and 2 here, those are pretty common constraints for when we're talking real world, because we don't deal with negative plants or negative miles or negative inches or whatever. Okay, so those are popular constraints. Okay, then the next thing, we know that we're covering up to 600 square feet. Okay, covering up to 600 square feet. In order to cover that, every Blue Lagoon covers 1.2 square feet. Every red, why doesn't it say it in the problem? Shoot, it doesn't say it here. I mistyped it. But every red covers 2 square feet. Okay, so then the raspberry red covers 2. And we need to cover 600 square feet. We're going to cover all the way up to 600 square feet. Okay. Then each plant costs $2.50, so we have to take the cost into account. So this one talks about the area, and the next one's going to talk about the cost. Okay. So the cost here is each one is $2.50. And the cost is going to be less than 1,000. So now we have some constraints. I'm going to get this graph, I'm going to get it set up, and we'll take a look at that. Okay, so just right there, I wanted to get our graph all set up. Now I know with that b greater than 0 and that r greater than or equal to 0, that locks me into this first quadrant where both values are positive. Okay, I'm going to make this blue and this red. Okay, so now I got two other functions still to graph. One of them says 1.2b plus 2r is less than or equal to 600. It's hard to graph a function like that, especially when you have to solve for y. Well, there's no y here, but let's use intercepts. Okay? Remember, in an intercept, we make one value equal to 0. So we could find the blue intercept by letting r equal 0. Okay? So 1.2b plus 2.20, so that's going to be wiped out, equals 600. Okay, so we're going to divide 600 by 1.2, and that's going to tell us what our intercept is. Okay? We get out our calculator. Hopefully you're doing this with me right now. Okay? And our intercept on the blue is over here at 500. Okay? We can go the same way and find the intercept of the red. 1.2 times 0 plus 2r. Okay? So we're going to divide 600 by 2. This line now has an intercept there. So we very, very carefully draw a beautifully straight line. Now we want to be less than, so we know we're going to be on the 0 side of that line. Okay? Then we got to figure out the last one. Same thing, I'm going to find both intercepts. Okay? This b intercept here. And these intercepts are going to be the same, but 2.50, let's find b first, plus 2.50 times 0. Okay? And 1,000 divided by 2.5 is going to be 400. Okay, so that means my other line is going to have its point at 400 for one of the intercepts. Find the other intercept, put in 0 for b, solve for r. And this intercept is 400 too. Okay? Now I have a line that looks something like this. But we got to have the overlap. Okay? Because this line follows this kind of a pattern. The overlap is like this. We have a quadrilateral with 4 corners. We have a corner at 0, 0. We have a corner at 0, 300. That means we use 300 of those red raspberry things. We have a corner at 400, 0, where we use 400 of the blue lagoons. And we have a third corner at 250, 150. Okay? So this third corner lives at 250, and my graph kind of sucks, but it's at 250 and 150. We're going to talk a little bit more about how to get those corners when you come to class. Okay? Now, those 4 corners, one of them has to be the maximum or the minimum, and that's where our linear programming actual process comes in. Now that we have a feasible region, we apply these ordered pairs to our objective function. Okay? And our objective function is the function or the equation that you're trying to maximize or minimize. And a lot of times it's because you want to make sure that your answers fit into a particular equation or solve or maximize a particular situation. You maybe have heard problems that say you want to maximize the area. That's a thing you do. You do this a lot in calculus actually too. Okay? But in this case, this is the equation that is being, sorry, I should add some words, is being maximized or minimized. So let's take this a step further here with looking at Jillian and her problem, because we have a function we're going to maximize for her. So if we take that Jillian situation a little bit further, one of Jillian's priorities for the green roof is to help control air pollution. So all of this planting is meant to control air pollution. She wants to maximize the amount of carbon dioxide the plants on the roofs absorb. Use the carbon dioxide absorption rates and the data from example 1, that's the picture we have right here, to find the number of each plant Jillian should plant. Okay, remember we had some maximum here, we had blue, we had a point here at 400, 0, we had a point at 250, 150, we had a point at 0, 300, and we had a point at 0, 0. Okay? What's nice about linear programming is that maximum or minimum has to live at one of those 4 vertices. You don't need to try every single point in this region. That would take you forever. What we like about linear programming is that our answer lives on one of those corners. One of those corners will be the maximum here. Okay? Now, what is our objective function? Well, we have to write that. What we know is that we're going to let C, we have a new variable to define, we're going to let C be the amount of carbon dioxide, CO2. Okay, we already know what B is and we already know what R is. Okay, but now we have to go through and, okay, maximize the carbon dioxide. Now the Blue Lagoon plant, it can do 1.4 pounds per year. So 1.4 times the number of blue plants is going to tell us how much carbon dioxide they can absorb. And then a raspberry one can do 2.1. And we want to make C as big as we possibly can. Okay? We have 4 ordered pairs to try. 0, 0, 0, 300, 250, 150, and 400, 0. So we got 4 we need to try. So we do the first one. 1.4, and I'm just going to do this one. 1, 2, 3, I'm just going to go around the horn. 4. Okay? Times 0 plus 2.1 times 0 equals C. Okay? So C here, I'm going to actually solve it instead of writing C. But this is just 0. If we don't plant any plants, we're not going to save the earth. Okay, that's not exactly what we're saying, but it's what I'm saying. Okay, what I mean is 0, 0, definitely not going to maximize it, but we need to try that point. If we were looking for the minimum, that may have been a good point. Okay, let's try point 2. 1.4 times 0 blues. Our blue is 0 because the ordered pair is 0, 300. Okay, plus 2.1 times 300 red guys. So we need to figure out exactly how much carbon dioxide those can absorb. Okay? And they will absorb 630 pounds, right? Pounds. Okay? 0 lumps. Okay, so we have a number. We want to beat that number. If we don't beat it, this is the maximum. But we still have a chance to beat it, so we have 2 more to try. 1.4, 250, plus 2.1, 150, and you all can do order of operations. You can do 1.4 times 250, you can do 2.1 times 150, and you can get 665. Okay, we've already beat it, so now we're thinking that maybe this is our best one, but still got one to try. Okay, we still have one that we need to get tried. And the last one, 1.4 times now 400 blue guys, plus 2.1 times 0 red guys. And when we sit at that particular point, or that combination, we're at 560 lumps. Our function, our objective function, the most carbon dioxide happens here, when we're at 250 and 150. So Jillian should plant 250 of the blue and 150 of the red. That's linear programming. That's kind of a long process, but we're going to talk about it and we're going to do some things to streamline it when you come to class. So I just hope you're able to take that all in and be ready to rock on 3.4.